Hey guys, welcome to today's lesson. Before we start, I just wanted to say that I really miss seeing you guys at school. This is just not the same trying to do this all from a computer, but as much as I miss you guys, I really look forward to seeing you in the hallways next year. I also wanted to take a moment and just thank you for all the work you've been doing. You guys have been doing a great job keeping up with the work. The effort really seems to be there still. You're still showing an interest in learning. And it's nothing that I didn't expect because you guys are awesome. But I just wanted to thank you anyway, because I'd imagine it's very challenging at times to keep the motivation up. So you guys are doing a great job and I appreciate it. Let's go ahead and get started. So the first thing I'd like to do is go over those two problems that you ended with on the last class. So one of them was verifying algebraically this identity. Anytime the two expressions are equivalent to each other is called an identity. So you're verifying this side is equal to that side. I'm going to guess most of you got a common denominator. And to get a common denominator, it's going to be 1 minus sign, 1 plus sign. That way, because this fraction, the only factor in the denominator is 1 minus sign. So since that can't be factored, that denominator itself is a factor. And this denominator itself is a factor. And since they're not a perfect match, you need both of those factors to make your LCD. So once you get that LCD, this time I did multiply out in the denominator because I recognized it was going to be a Pythagorean identity. And you get down to your answer pretty quickly. If you need further explanation on any of those steps, just let me know. Another idea you might have had, because I introduced the strategy of creating a Pythagorean identity, is you may have thought about creating a Pythagorean identity in each of those fractions instead. So to create the Pythagorean here, you'd multiply by 1 plus sign over 1 plus sign. And to create the Pythagorean identity in this one, you'd multiply by 1 minus sign over 1 minus sign. The funny thing is, even if you thought about it that other way, you actually end up with pretty much all the same work. So you might have thought about it a very different way than one of your peers and ended up with all the same work anyway. All right, so that was verify algebraically. If you didn't get that all the way through, that's okay. Again, this chapter is much more challenging, in my opinion, than the previous chapters. It's okay not to get everything on the first try. So just ask questions if you have them, and just keep being aware of that. All right, next, you guys did a graphing calculator problem, and it was a matching, and the correct answer for that one should be C. So when you graphed this expression, you should get C. If you didn't get that, you can take out a calculator real quick, and here's how you could graph that in the calculator. So to put this in the calculator, you're going to have to do 1 over sine for cosecant. You'll have to square it, and you must have parentheses around the x plus 1. The most common mistake on this one is usually forgetting the parentheses around the x plus 1. And here are 3 different variations that you could have, and there are others, but these are the most common 3. So 3 parentheses times the 1 over sine squared, or you can not have parentheses there and just put the times symbol. And since this is 3 times 1 over sine squared, so that's 3 times 1 over sine squared for that part, that's the same as having 3 over sine squared for that part. I'm not looking at the denominator right now. So 3 times 1 over sine squared is the same as 3 over sine squared. So some of you may have not bothered with the 1 there and just condensed it a little bit more. Okay. Now let's continue on to today's lesson. And for today's lesson, I had all these notes written up, and I thought I would share them with you. You could print them or read them yourself, and that would make it a little quicker to go through it together, because I think you're going to pick this lesson up pretty quickly. Most students find it easier than section 5152. So we're looking at section 5.3, and we're going to be solving trig equations. So here's our first example, all done for you. So we're finding all solutions between 0 and 2 pi. According to this, 0 is acceptable as an answer, 2 pi is off limits, because this inequality is inclusive because it has or equal to, and this one is strict. Sometimes instead of this inequality, you'll see in an interval notation instead. And what you want to do for some of the basic ones is you want to isolate the trig function. So move this 3 over by adding, move this 3 over by dividing, and this problem should look familiar. You've solved this many times, it just usually has theta. So can you picture a theta right there instead of an x? You've solved this problem before. So if you like reference angles and quadrants, you can use your special triangles to determine your reference angle. And since tangent's positive, you want the answers in quadrants 1 and 4. You can draw those sketches if you want or if you need to. And these should be the 2 answers you get. If you're a unit circle person, you can draw the first quadrant of the unit circle, find out that you're using pi/4 as a reference angle, and then use all students take calculus to get the quadrants, or some of you can visualize the entire unit circle. So you actually can figure out that if you put the y coordinate over the x, you're going to get 1 for these 2 angles. So any method you use to solve that is fine. And just to note here, this is the reference angle for x. If you write theta prime, that's okay. There's technically no theta in this problem, but we're so used to writing theta prime for reference angle. So if you do that, that's okay. But one thing you don't want to do, because you might be thinking, oh, I know what to do to make it right. I'll use x prime because that's the reference angle for x. You don't want to do that. X prime next year means something in calculus class, so I would avoid that. So either write the word reference angle or write theta prime, even though there's no theta in the problem, or just don't label it, but avoid x prime so you don't get messed up for next year. Okay, next one. Next one, I labeled this example B, and this time we have sine in 2 different places, so we can combine our matching trig functions to start. It's like combining like terms. So let's move this sine to the other side. 6 sine minus 1 sine is 5 sine. Then you can isolate your trig function. And if you don't have a reference angle of 30, 60, or 45, because we're doing all this without a calculator today, then you're going to try your quadrant angles to find out if you have an answer or 2. And sometimes you'll get 2 answers, sometimes you'll get 1 answer. We're actually going to see problems where you can have 3 answers and 4 answers, 5 answers, 6 answers. We can make them up with any amount of answers. All right. Next is example C. And for example C, there's a few things to be learned in this example. So we do want to start again by isolating the trig function. So we do want to get secant by itself, but here secant is not by itself because it has squared. So to get rid of squared, use the square root on both sides. And sometimes people don't see from this line that like square root's going to make the squared go away. So if you think about what secant squared x means, it means secant x being squared. So if it helps you to rewrite it like this, then you'll say, oh yeah, to get rid of squared, I definitely take square root. So sometimes it's a little tricky with that notation. But if you think about it as secant x being squared, usually makes a little more sense that you're taking square root of both sides. Don't forget that plus minus. Now to solve for where secant x is plus or minus radical 2. To get the reference angle, you can, if you're comfortable with secant, you can use the unit circle or draw your 45, 45, 90 and your 30, 60, 90 and figure out where secant's radical 2. If you're a little uncomfortable with secant, then you can switch over to the reciprocal, which is cosine. So if secant is plus or minus radical 2, then cosine is plus or minus 1 over that, which is plus or minus radical 2 over 2 after you simplify this fraction by rationalizing the denominator. So if this looks more familiar, when you look at that, if you say, oh yeah, that's pi/4, and it's easier for you than working with secant, then switch it over to cosine, no problem. So if you're working on a problem that has cosecant, you can switch it to sine. If you're working on a problem with cotangent, you can use the reciprocal and do tangent instead. Okay, so that's the reference angle. Now we have 4 answers because we've used all 4 quadrants here. The reason we can use all 4 quadrants is because we want secant to be either positive radical 2 or negative radical 2. We're happy either way. So secant will be positive in quadrants 1 and 4, and we like that. And secant will be negative in quadrants 2 and 3, which is also acceptable. So that's why we have all 4 answers this time. Just a quick note, a lot of times what happens when I'm teaching this section is students might forget how to do a certain part of this. So if that happens to you, just reach out and ask. I can always make you a little video or answer your questions. Because even though we've learned how to do this part, sometimes students just draw a blank. They say, wait, how did you get pi/4? Or how did you know that secant would be positive in quadrants 1 and 4? So if there's anything I do that you miss out on, just ask, because that's what we would do in class. Okay, that happens a lot when we're in class together doing this unit. Okay, one more of these problems that are already written out for you. For this problem, we can't just square root this because we have sine squared and we have sine, and you can't combine them. So if you were thinking about combining them, think of this as 2x squared minus x. You can't combine 2x squared minus x. But what you can do is you can factor. So if you can factor this straight away, that's great if you want to write it in terms of x. And you guys were kind of split on that. About half the class was kind of like, I'm just going to factor. About half the class says I like to write it as x first. Either way is fine. And then you should get these two factors. Now, if we were solving this, we would set each factor equal to 0 and solve. So along those same lines, we're going to set each factor here, even though it has sine in it, equal to 0 and solve. Set this one equal to 0 and solve. If you have any questions on these steps, just ask, please. Okay, now what you're going to do, please, is you're going to try the 4 problems that I have on the bottom. So go ahead and try 1, 2, 3, 4, and then you can continue the Edpuzzle, and I'll ask you about the answers, and I'll provide you the solutions. Okay, here's the solution for number 1. For number 1, you should get x equals pi. If you didn't get that, the most common mistake would be when you were doing your points on the unit circle, flipping those. So I can't tell you how often I see somebody, instead of -1, 0 here, they put 0, -1. And I've done it myself, and I wouldn't be surprised if you guys have done it as well. Very common mistake. Okay, for number 2, you should end up with 4 answers, and it's all the ones that have pi over 3 as a reference angle. Okay, here's number 3. Number 3 should only have 2 answers. You should get pi over 6 and 11 pi over 6. If you got 4 answers, I think I know what happened. When you saw the square root, you thought, oh, I need plus or minus. You don't want plus or minus here. Here's why. The radical was in the problem to start with. So whatever sign is in front of it is the one we want there. So if the radical is in the problem to start, we actually have no right to put plus or minus. We have no reason to do that. In number 2, on the other hand, there was no square root when we started. We took the square root of both sides. We introduced the square root, so we must put the plus minus. So that's when you put the plus minus. If there's no square root and you take the square root of both sides, you have to put plus minus. If the square root is in the problem when we start, then you have no right to put plus minus. Just whatever signs are there, work with them. Okay, the other really common mistake on this one is using pi over 3 as a reference angle instead of pi over 6. If I'm going to make a mistake, that's usually the one I make, swapping 30 and 60 by accident. Okay, and number 4. When you factor, you should get these 2 factors. Set each one equal to 0. I prefer sine over cosecant myself, so I switched them over to sine, and these are the 3 answers I get. And when you write your answers, by the way, you can write them in any order. So if you wrote 3 pi over 2, then this one, that's fine. You can write this one first, that one second. When you go back over here to number 3, anyway, it's fine. Okay, now that you've gotten some practice, let's continue on with 2 more problems that will have kind of slightly different techniques that we need to use. So I'm calling this example E. I don't know if you noticed, but I've been using letters and numbers just so that if you ask questions, it's really easy for me to tell. I don't have to say, was that number 1 in the practice or number 1 in the examples? All right. So I'm going to call this example E. Let's find all solutions. Here I use 0 to 2 pi in interval notation. And this is the problem we have. So think about your first step. And a lot of people are probably thinking of dividing both sides by sine. You don't want to go that route. You'll actually lose some answers, and we'll see that as we go. So first, let's show you how to do this, and then I'll show you why you should not divide by sine over sine to start. Divide by sine on both sides to start. So if we think about this, we have sine squared x equals sine x. And I wanted to write that with x's instead. So in order to solve, if we have the structure something squared equals that same something to the first power, what we want to do is we want to move this x over and factor. That is a correct way of solving. You should not start this problem by dividing both sides by x, and we'll see why after we solve this one correctly. Okay, so this would give us 2 answers. Now over here, I want to follow that same idea. If we move this sign over, then we can factor. And when you factor, you always want 0 on the other side. So if you have a number over here that's not 0, you don't want to factor yet. So if this were a 1 or a 5 or a 2, you'd move it over before you try to factor. Okay, always have to have 0. Must be 0. Big deal. So as long as you have 0 there, you can now set each factor equal to 0 and solve each of these, what I call like mini equations. So sine of x is going to be 0 at this angle and at pi. So for this angle, should I call it 0 or should I call it 2 pi? I should use 0. 2 pi is also a solution here, but according to the instructions, 2 pi is off limits. So if we have to choose between 0 or 2 pi for that angle, we're going to call it 0. And pi also works because sine of pi would be 0 as well. And then over here, I have sine of x equals 1. That's also a quadrant angle. That's going to be pi over 2. So this equation actually ends up with 3 solutions. So as I've mentioned, we've now seen examples with 1 solution, 2 solutions, 3 solutions, 4 solutions. Kind of anything can happen. You could even have 5 and 6 solutions. You could have no solution as well. So this is a correct way to solve this. Now, as far as why you don't want to start the problem by dividing both sides by sine. Well, let me take you over here. See how this is degree 2? By the fundamental theorem of algebra, do you remember that? If you have a polynomial, whatever the degree is how many answers you should have. So like if you had a degree 3 equation, you should have 3 answers. If you have a degree 4 equation, you should have 4 answers, and so on. So since this is degree 2 and it's a polynomial, we have to have 2 answers. If we were to start this problem by dividing both sides by x, what would happen is this would become x, this would become 1, and we're missing an entire solution. So we only got this answer, we're missing this one entirely. And that's because what happened was when we divided both sides by x, we changed the degree of the problem, and x reduced out. We went from a degree 2 to a degree 1. So what the lesson to remember here is you don't want to divide both sides by x if an x reduces out, because you're probably going to lose solutions. I'm going to say it again in case you want to write it. Don't divide both sides by x if it reduces out, because you run the risk of losing solutions. So same deal with this guy here. Now, by the way, this is not a polynomial because sine is involved. That's not a polynomial. So the fundamental theorem of algebra does not hold. Remember how I said this has to have 2 answers, and if it were x third, it would have to have 3 answers and so on? That does not work with trig. You cannot predict at the beginning how many answers. So no matter what powers are in there, you could have 1 answer, 2 answers, 3 answers, 4 answers, and so on. So fundamental theorem of algebra is for polynomials, does not apply when you have trig. Okay, so if we were to start this problem by dividing both sides by sine, like you may have been tempted to do in the very beginning, a sine reduces out. This becomes sine to the first, that equals 1, and the only answer to that equation is pi over 2. You'd be missing out on 0 and pi. So that's why, even though it's really tempting, what you want to do with this problem is you want to start by moving everything over and factoring. So once again, you just like up here, you can't divide by x on both sides if it reduces out. Do not divide both sides by a trig function if it reduces out, because you run the risk of losing solutions. So it's not just a rule for sine, but it's for all the trig functions. Don't divide both sides by a trig function that has an x in it if it reduces out, because you run the risk of losing answers. Okay, and let's move on to our next one. So we're going to go ahead and solve this one. I'll let you think, see if you have any thoughts on how you might go about that. And let's look at a couple ways to do it. So for this problem, you might be thinking, let's move the 3 cosine squared over and try to factor. That's a really good idea, but it doesn't factor. It doesn't factor with rational numbers. It doesn't factor with nice numbers. So we need to try something else. So another thought you might have is maybe Pythagorean identities. That might not be the idea you had. We'll see a completely different way in a minute. So you see how you have sine squared and you have cosine squared? If possible, we prefer trig functions to match in an equation. We don't really like to have two different ones. So what we could do is use a Pythagorean identity and either replace sine squared with 1 minus cosine squared or replace cosine squared with 1 minus sine squared. Either way is fine. Either way works. You're going to get the same answers. So let's replace sine squared with 1 minus cosine squared, just because. So I'm going to replace this with 1 minus cosine squared. And now that I have all cosine squareds, I can actually combine these. So I can move the cosine squared to the other side. I have all my cosine squareds together. I'm going to move that 4 over. It's not the only way to do it. I'm going to take the square root of both sides. Squared and square root cancel. The square root of 1/4 is the square root of 1 over the square root of 4. That's 1/2. Notice I have the plus or minus in every step. If you want to have your notation correct, as soon as you bring in the square root, you put the plus minus. Don't wait till down here, and include it in every step. So cosine being plus or minus 1/2, the reference angle for that is going to be pi over 3, and it's totally okay if it takes you a moment longer than that. You don't have to do it that fast. And the quadrants are all 4 because we're happy whether cosine is positive or cosine is negative. So the answers we get are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And again, you don't have to do that part this fast either. So if you need to make a sketch and show that this is the angle we're looking for in quadrant 2 and the reference angle is pi over 3, and think, okay, pi minus pi over 3 is 2 pi over 3, that's fine. But since I know you guys know how to solve this, do the lessons at this point, I tend to kind of go a little faster through that part. And that's what I would do if we were in class together as well, because I know you know how to do that. So when you do your practice, you can practice that. But this way we can continue on to more types of problems, or in this case, different ways to solve this one. Okay, so that's our set of answers here. And this was one way to do it. And just to kind of show you some other things, if from here, you wanted to move the cosine squared to the other side, this time it actually does factor. That's a difference of 2 squares. This type doesn't always factor. It happens to factor because this is a 1 and a 4 and that's squared. And it's a minus in between. Okay, but this one happens to factor. This factor will give you cosine x equals 1/2. And this factor will give you cosine x equals negative 1/2, so you do get the same answers. And also to mention from the beginning, I chose for us to change sine squared to 1 minus cosine squared. If you chose at the beginning to change cosine squared using a Pythagorean identity into 1 minus sine squared, that's totally fine, but you have to be careful because you change that one term to 2 terms and there's a factor out front, so you have to distribute. And then you could continue the problem from there. So what you would end up with is you'd end up with sine x equals plus or minus radical 3 over 2, which gives you these same 4 answers. So this I still consider just one way to do the problem. Like I said at the beginning, there's a completely different way to start this, where it doesn't even involve using a Pythagorean identity. Okay, so let's try this problem one more time. And when you solve these on your own, you don't have to do this 3 times. Just in the lesson, I want to show you some different options in case you were thinking of something different, or just to inspire you to think about all the different ways you might do this. So here's another way to do this. You can divide both sides by cosine squared, and that's going to make sine squared over cosine squared, which you can replace with tangent squared. So here that reduces, and here I get sine squared over cosine squared, which gets replaced with tangent squared. And when you set both sides, take the square root of both sides, you're going to get plus or minus radical 3. And if you take the time to find the reference angle and figure out that you want all 3 quadrants because you're happy whether tangent is positive or negative, you get the same 4 answers that we got with the other method. And I just want to address a question you might have, because a couple minutes ago I made a really big deal about this problem, example E. I said, okay, when you start this, you cannot divide both sides by sine. No, 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 you can't do that. Okay. And then what did I do over here? I said, oh, I'm going to divide both sides by cosine squared. Why not? Okay, well, here's the difference. When I divide both sides by cosine squared here, does cosine squared leave the problem? No, it's still here. It just moved to the other side. I know it reduces here, but cosine squared didn't leave the problem entirely. It's still there. It didn't reduce out of the problem. So if you go back and watch the video, what I've said over here was I didn't say you can't divide by sine on both sides. I didn't say you can't divide by a trig function on both sides. I said you can't divide by a trig function on both sides if it reduces out of the problem, because then you can risk losing solutions. So because this reduces from a second power down to a first power, that's why that's dangerous. For this problem, we didn't reduce cosine squared out, we just moved it to the other side. So that's why that's okay. And last thing on this one, for anyone who is thinking, well, you divided both sides by cosine squared, could you have divided both sides by sine squared instead? Yes. Sine squared over sine squared is 1, not 0. Make sure that becomes 1. And then if you have cosine squared over sine squared, that's cotangent squared. And if you do this work, you'll get cotangent equals plus or minus radical 3 over 3, which gives you the same 4 answers. Okay, and I know I zipped through that part, but again, I feel confident that you could do that part on your own with a little more time. So even if we were in class, I would zip through that part just to show you like the new stuff, okay? So that'll do it for today's lesson. Thanks for watching. And tomorrow is going to be mostly a practice day. I'll show you one little new thing and then all practice. Thanks, guys. Bye-bye.